Which one of the following is the name of the functional group of propane 1-ol? This is a very basic question. Sticking to the basics, the definitions. We are not really applying anything here. So you should know that the answer to 1.1 is C. The name of the functional group of propane 1-ol and alcohol is hydroxyl. 1.2, the organic compound C2H4 is converted to an alkane as shown in the reaction below. So it is an alkene to an alkane. So we know that that is hydrogenation. Which one of the following is a suitable catalyst for this reaction? Again, sticking to the basics. The answer to 1.2 is B, platinum. 1.3, which one of the following statements always apply to compounds that are structural isomers of one another? So the key word here is always. It has to always apply. Let's take a look at Roman figure 1. They belong to the same homologous series. Not necessarily, because ketones and aldehydes can be structural isomers of each other. Acids and esters as well can be structural isomers of each other. Roman figure 2, they have the same structural formula. That is not true. There's no way that can be true, because by definition, they're structural isomers if they're different in structure. And then Roman figure 3, they have the same molecular formula. Obviously, that has to be always true for them to be structural isomers. 1.4, magnesium ribbon of mass 2 kgs, 2 grams reacts with excess hydrochloric acid of concentration 0.1 mole per decimeter cube at 20 degrees Celsius. Which one of the following changes will not, the keyword here is not, increase the initial rate of the reaction? Using 2 grams of powdered magnesium. We're looking for will not. Obviously, this will increase the rate of reaction because we have increased the surface area. Increasing the temperature will increase the rate of reaction because we're going to have more effective collisions per unit time. And then C, using a longer piece of magnesium ribbon. So, slightly confusing question, because there's an assumption that we have to make. Using a longer piece of the magnesium ribbon. Okay, so no, it is precise. I was missing the point. It's not saying using a longer piece of magnesium ribbon. No, of the magnesium ribbon. So there's an increase in mass here of the initial mass of the magnesium ribbon. So if that is the case, obviously we are going to have an increase in the rate of reaction because we have increased the number of moles initially of the magnesium ribbon. If we use a longer piece of magnesium ribbon, then we're going to have more surface area on the exposed areas of the piece, right? D, doubling the volume of the hydrochloric acid used. The hydrochloric acid is in excess, so we already have excess number of moles that are ready to react. So when we increase the volume of the hydrochloric acid, which is in excess, it's not going to increase the initial rate of the reaction. So the answer to 1.4 is D. There we go. 1.5, the following reaction reaches equilibrium in a closed container. The reaction rate versus time for the reaction is given below. So take a look at the reaction. On the left hand side, we have 1 mole of gas. On the right hand side, we have 1 mole of gas as well. And then the sulfur, which is solid. What change was made to the system at time T1? The pressure was increased at a constant temperature. 1.5, that is actually the answer. The answer is A. Right, because as you can see, when there's an increase in the volume, the system cannot respond accordingly as you decrease the volume, right? So the rate of reaction of forward and reverse, they just increase equally so, because we have equal numbers of gases on the left hand side and the right hand side. And then B, the volume of the container was increased. Obviously that would decrease the rate of reaction. The temperature was increased. If there was an increase in temperature, it should have favored the reaction that reduces the temperature. It should have favored endothermic reaction more than it does the exothermic reaction. So we cannot have both forward and reverse reaction going up in that manner. And then more hydrogen was added to the system. Should have favored the forward reaction. Yeah, so that is 1.5. 1.6. A hypothetical endothermic reaction is given below. The activation energy of the reverse reaction is 50 kilojoules per mole. Which one of the following is possible for the reaction above? So I took a lot of time in this question because I had missed endothermic, right? So it was very hard to answer when I have missed that it is endothermic. But then I reread the question and then it made sense. I could cancel out some things because now I know that the reaction is endothermic. So if the reaction is endothermic, it looks like something like this. These are the reactants, obviously. These are the products. All right. And then this is some enthalpy change. Okay. And then it says the activation energy for the reverse reaction is 50 kilojoules. Kilojoules per mole. So we have 50 kilojoules per mole there. Right. So A says, or which one of the following is possible? So A says the heat of reaction for the reaction, the heat of the reaction is plus 70 kilojoules per mole. Makes sense? Makes sense. It can be true. It is very much possible because we know that it is supposed to be positive because the heat of reaction is energy of products minus energy of reactions, and we know that this is an endothermic reaction. So A is very much possible. What about B? The activation energy for the forward reaction is 50 kilojoules per mole. That cannot be the case. We cannot have the activation energy of the forward and the reverse being equal to each other and then conclude that the reaction is endothermic. So B cannot be correct, right? And then C, the energy of the activated complex is 40 kilojoules. Can that be true? Let's make sense of that. Okay, if we have 40 here as the energy of the activated complex, and then the enthalpy or the activation energy for the reverse reaction is 50, then it means that we have 10 kilojoules there. Not 10, but minus 10 rather. We have minus 10. We have minus 10 kilojoules there. And then what would be the... Does that make sense? Let's think about whether that makes sense or not. If that is minus 10, then the energy of the reactants would have to be less than that of the products. So I'm conflicted on C. Let me take a look at D. We'll come back and look at A and C. And then D says the activation energy for the forward reaction is 40 kilojoules per mole. So if it's 40 and the activated... if it is 40 and then that of the reverse is 50, it does not make sense. It cannot happen. Of the reverse, the activation energy of the reverse cannot be greater than of the forward reaction if the reaction is endothermic. Yeah, it doesn't make sense that from here to here we would have 40 when from here to here we have 50. So this option does not make any sense. Is it possible for the potential energy to be negative in these graphs? Not so sure, but it is very much possible for the heat of reaction to be plus 70 kilojoules per mole. There's nothing wrong there. So I'm going with C, not with C, but with A in 1.6. And then 1.7, the products of the reaction between a metal oxide and an acid are... So here we just stick into the basics, a salt and water, just the definition. 1.8, the concentration of each of the four solutions below is 0.1 mole per decimeter cube. Which one of the following correctly places the solutions in order of increase in pH? So we have NaOH, which is a very strong base. So we should be looking at A and B only now because NaOH should have a higher pH than everything else there. Okay, and then NH3 is a base, NH3 is a base. So now we are deciding between H2CO3 and what? And HNO3. HNO3 is a stronger base compared to H2CO3. So the answer to 1.8 should be B, therefore. So 1.8, the answer is B. It is not A. 1.9, we have a galvanic cell with Fe, Fe2 plus and nickel. Which one of the following statements is correct for this cell? So there's something that we need to figure out first. We need to figure out where is where before we answer this question. We need to know where the nickel is and where the iron is in terms of anode and cathode. So I'm paging through my table 4b here of standard reduction potential. So obviously I have anode and cathode. Okay, So on my table, I'm looking for Fe, there it is, and then I'm looking for nickel. So nickel is a stronger reducing agent. So nickel is at the anode, and then Fe, it is a stronger oxidizing agent. So it is at the cathode, right? Okay, so let's carry on and see what is happening. So this is the anode, this is the cathode. A says Ni to the 2 plus is reduced. Ni is at the anode. At the anode, oxidation is taking place, so that is not the case. And then B says Ni2 plus is oxidized. Ni2 plus, that is not the case, right? Ni2 plus is just the ion that is formed when oxidation takes place. And then C says platinum is the electrode at the cathode. At the cathode, we have Fe to the 2 plus and then Fe to the 3 plus, which are both in aqueous solutions. So C makes sense for us to have platinum at the cathode, as it is inert. It is not ready to react. It does not really like to react. And then Ni is the electrode at the cathode. We've determined that not to be true. So the answer here is C. And then 1.10, the setup for electroplating an iron metal with silver is shown in the simplified diagram below. Okay, so at the cathode, we need the metal that we are electroplating, and then at the anode, we need the silver, obviously, so that oxidation can be taken place, and then the iron metal can get coated through reduction at the cathode. Okay, so which one of the following combinations for the anode and the reaction at the cathode is correct? So let's start here. At the anode, we need the silver. So this is anode, right? And then at the cathode, we need the iron metal so that it can be coated through reduction. So anode, silver rod. So we're only looking at A and C. Or not iron metal, but silver rod. So we're looking at B and D in this case. And then reaction at the cathode, this way the reduction is taking place, right? We're going to have Ag plus an electron giving us Ag. So that is the answer to 1.10. It is D, therefore. Let me know which question you want me to do next in the comments. Do you have any other opinions? Did you get anything different from what I'm getting? Let me know in the comments. Write down the letter that represents an alcohol. Let's take a look. We have A, B, C, D, E, F, G. We're looking for an alcohol. A clearly is not. B is not because that is a haloalkane. And then C looks like an aldehyde, but take a look at D. D looks like an alcohol. So let's investigate. In D, we have C4H10O. If we write that in terms of the general formula, we would have CnH2n. H2n plus 1 OH. Makes sense. So 2.1.1 is D, that is alcohol. And then 2.1.2, two compounds that are functional isomers of one another. So functional isomer of one another, either aldehyde and ketone or esters and carboxylic acids. So let's take a look. But they need to have the same molecular formula, that is. So G is an alkene, B haloalkane, D obviously that is an alcohol, and then F is an alkane, E is an alkane as well. So are we only left with A and C? I think we are. So let's take a look at A and C. 1, 2, 3, 4, 5. So that is C5, and then it is a ketone. And then let's take a look at C. 1, 2, 3, 4, 5. So C, as it ends, we have a carbon with 2 hydrogens, a carbon double bond oxygen, hydrogen. So the answer therefore is A, C. 2.1.2, we have 2 compounds that are functional isomers. 2.1.3, 2 compounds that belong to the same homologous series. So we want the same homologous series. So E, we've said that E is an alkane, right? So E is an alkane, F is pentane. So same homologous series, they're both alkenes. So E, and F, they belong to the same homologous series. And then question 2.2.1, IUPAC name of compound A. So obviously, sticking to the basics, we need the longest carbon chain. So that seems like it. Let's check 1, 2, 3, 4 carbons, and then if we go straight, we have 1, 2, 3, 4 carbons. So that is the longest carbon chain. So we have 1, 2, 3, 4, 5. So we have pen 10, and then we have to start numbering our carbons from the side closest to the functional group. So 1, 2. When we start from the bottom, we have 1, 2, 3. So we have to start numbering from the left hand side, of which the double bond oxygen will be on the second carbon. So we have pen 10, 2, O, and E, right? And then we have a branch on the third carbon. So that will be 3-methyl pentane 2 on. So 1, 2, 3. Wait a minute. 1, 2, 3, 4. That is actually bute. What am I doing? 1, 2, 3, 4. Okay, and then when you go straight, you have bute as well. So almost got this wrong. So butane 2 on. 1, 2, 3, 4. And then the functional group is on the second carbon and the branch is on the third. Okay, I think we're fine now. 2.3.1. No, 2.2.1. What about 2.2? IUPAC name of compound B. So we have a haloalkane. So let's find the longest carbon chain. So 1, 2, 3, 4, 5, 6. If we go up, we have 1, 2, 3, 4, 5, 6, 7. So the longest carbon chain is 7 there, because if we go up here, it would still be 7. So let me see if I can highlight it. This is our longest carbon chain. Just to verify, this is 1, this is 2, this is 3, this is 4, 5, 6, 7. Okay, so pent is, not pent, but 7. 7 is hept, so we have heptane because it is a haloalkane. So we need to actually number our carbons from the side that makes the most sense. So, not really. Let's just start numbering from the left and start numbering from the right and see which option gives us the smallest number, because that's what we are looking for ultimately. So on the second carbon here, so this would be a branch on the fifth carbon. But between methyl and chloro, we have to start with chloro, right? So we say 2 dash chloro dash 2,5 dimethyl heptane. So let me verify. 2 chloro, it is there. 2.5 dimethyl heptane. That seems fine. If we start numbering from the other side, what are we gonna have? We would have 5 chloro, right? And then we would have 1, 2, 3. Would have 3 and 5 methyl. Yeah, so that does not work. We have to start numbering from the left. That is our better option. So that is the answer to 2.2.2. IUPAC name of compound G. So we need the longest carbon chain once more. So let's take a look. 1, 2, 3. If we go down, 4, 5, 6. Let's check. 1, 2, 3, 4, 5, 6. The other side, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. I think I may be with that. But we have to include the functional group though. Are we including the functional group in this path? Okay, let me take this route, of which I'm gonna have 1, 2, 3, 4, 5, 6. That would be 6 carbons. Seems to work. We have to start numbering closer to the functional group here. We don't have a choice. So 6 would be hex, and then the double bond is on the second carbon, so eggs 2 in 1 2 3 4 5 6 1 2. So yeah, the double bond is on the second carbon, and then the branch, where's the branch? The branch is on the second carbon, so we have 2 dash or methyl. No, we cannot start with that. We have to start with the one on the third carbon because it is ethyl. So we have 3 dash ethyl dash 2 dash methyl, because alphabetical order is important when we actually organize the branches. Alphabetical order is important. So let's just verify that we have done the correct thing. So how many carbons? 1 2 3 4 5 6 eggs. Double bond on the second carbon. We have a branch on the second carbon, which is methyl, and then on the third carbon we have ethyl. Maybe with that. And then let's check that first one, 2.2.2, just to make sure that everything is clear. We were looking for the name of compound B. So that is 1 2 3 4 5 6 7 heptane, branch on the second carbon, and one is chloro, the other one is methyl, but then we have another methyl on the fifth carbon. Looks good. I think we are looking for the okay, we've named G now. We named A, we named B and G. Okay, so 2.2.4, structural formula of two straight chain oppositional isomers of compound D. Compound D. So compound D, 1 2 3 4. We have OH. We've already deduced that is an alcohol, right? So positional isomer, same molecular formula, different position of the functional group. So the functional group here is on the first carbon, and then the other option, therefore, we should just change the position of the functional group. So from the third carbon, so from the first, let's say, to the second carbon. Okay, there we go. That would be the two structures of the functional, of the positional isomers. 2.3, compound E, C3H8 reacts with oxygen according to the balance equation. A combustion reaction. Initially, 8 centimeter cube of compound E and 50 centimeter cube of oxygen were injected into a container of adjustable volume and allowed to react. Rather than the name for this type of reaction, it is a combustion reaction. 2.3.2, calculate the total volume of the gases present in the container at the end of the reaction. So we need to figure out which one is the limiting, and then we're going to use the limiting to calculate the volume of CO2 and the volume of HO2. So how are we going to do that? So we have compound E and O2, right? We have compound E and O2. So we're going to find the number of moles of the two. So let me check on my question paper what VM is given as molar gas volume. That is 22.4 decimeter cube, right? Yeah. So I'm going to have 8 times 10 to the minus 3 times 10 to the minus 3 is the same thing as dividing by 1000, and then divided by 22.4. I must write the formula first, by the way. V is equals to VM, right? So that I can get a mark for the formula. 8 times 10 minus 3 divided by 22.4. I want to write this in scientific because there's a lot of decimals. So this is 3.5714 times 10 to the minus 4. On the other side, we have 50 over 22.4. That is 50 times 10 to the minus 3, by the way. So 50 times 10 to the minus 3 divided by 22.4. This is 2.2321 times 10 to the minus 3 moles. So in order to find which one is in excess, we need to divide these two numbers by their balancing coefficients. We know that it is 1:5, right? The balancing coefficient of E is 1, that of O2 is 5. So when we divide 3.5914 by 1, it's still 3.5914 times 10 to the minus 4. Is it 59 or 57? I'm going to have to check that again if I am to use it in other calculations. So I divide the answer that side by 5, as it is the balancing coefficient. I get 4.4643 times 10 to the minus 4 moles. So this is the limiting, because it is less than that of O2 when we divide them by their balancing coefficients. Don't be surprised by this method. If you use the basic method that we use to find the limiting reactant, it is completely fine. Yeah, some kids just showed me this method and it works. Yeah, but if you stick to the basics, don't worry, you'll be perfectly fine. So this is what I'm going to use to calculate what do we call this? To calculate the volume of the CO2 and H2O produced. Right. So volume to volume, not volume to volume, but gas to gas, we can use the mole ratio, but use gas instead because they are all gases. We don't have to go to number of moles first and then calculate the volume. We can just use volume embedded in mole ratio. Okay, so let's do that. 8 times 10 to the minus 3 over 22.4. I'm just verifying whether this is 57 or 59. It is 57. So now the volume of E is to the volume of CO2, that is 1 is to 3. So here we have 3.5714 times 10 to the minus 4. So here we're going to have what? So I just need to multiply that by 3. 1.0714 times 10 to the minus 3 decimeter. Oh, okay, no, I'm contradicting myself. I've used the number of moles here. I can just use the volume instead of the number of moles. Yeah, that's what I was proposing up there. Because if I calculate the number of moles, I'm going to have to then multiply it again by the volume, which I don't want to do. So I can use 8 centimeter to the 8 centimeter cube. I can use 8 centimeter cube here actually. So it will be just 8 times 3, which is 24 centimeter cube. So that is the volume of CO2. And then the volume of E is to the volume of H2O, 8 times 10, not 8 times 10 because I'm using centimeter as it is. 8 centimeter cube is to, I'm skipping steps, why? 1 is to 4, the balancing coefficient first, and then this is 8 centimeter cube. And then now we just have 8 multiplied by 4, which is 32 centimeter cube. So VT, the total volume, is 24 plus 32, which is equals to 56 centimeter cube, which is equals to 56 times 10 to the minus 3 decimeter cube. That is 2.3.2. Identify the two homologous series to which these compounds belong. Let's take a look. Two bottles contain compounds A and B with the same molecular formula, C4H8O2. These compounds are straight chain organic molecules that belong to two different homologous series. The balloon points are used to distinguish between the two compounds. 3.2. Identify the two homologous series to which these compounds belong. So you can see the general formula. We have O2. That only happens when we have carboxylic acids. So carboxylic acids and esters. Right. So that is the answer to 3.2. Identify the two homologous series to which these compounds belong. Carboxylic acids and esters. At this point, we don't know which is which. We don't have to specify. The following are vapor pressures of these compounds at a given temperature. So compound A has a vapor pressure of 0.071 kilopascals, and compound B has a vapor pressure of 9.7 kilopascals. So we know that the higher the boiling point, the lower the vapor pressure. So the compound with the vapor pressure has to be the carboxylic acid. So this is an acid. And the compound with a higher vapor pressure have to be an ester, a compound with the weaker intermolecular forces between the two. So 3.3.1 structural formula of compound A. So 3.3.1, we know that compound A is a carboxylic acid with 4 carbons. So we're going to have 1, 2, 3, 4. And then we have double bond oxygen, OH. Everything else, that is just hydrogen. So that is the structural formula of compound A. Am I missing something? 1, 2, 3, 4 bonds. Okay, we are happy with that. 3.3.2 IUPAC name for a possible compound B. So compound B is an ester with 4 carbons. So it can be ethyl ethanoate. It can also be propyl methanoate. It can be methyl propanoate. Those are some of the options that we have. I think those are all the options. Yeah, I think we have about 3 options. But anyway, stories. 3.4.1. Write down the strongest type of van der Waals forces between the molecules in compound A. So compound A is an acid. So the strongest intermolecular force is hydrogen bonding. Therefore, hydrogen bonding. And then compound B, strongest intermolecular forces in esters is dipole-dipole. So that is the answer to 3.4.2. Dipole-dipole. 3.5. Which compound A or B has a higher boiling point? Give a reason for the answer by referring to the strength of the intermolecular forces. So between A and B, A has a higher boiling point. It has stronger intermolecular forces, hydrogen bonding, right? Greater than the dipole-dipole in compound B. 3.6. The boiling point of compound A is measured again on another day when the atmospheric pressure is much lower. How will the boiling point of this compound now be affected? Choose from increases, decreases, or remains the same. Let me know in the comments. What's your answer to 3.6? The boiling point of compound A in a different day with a lower ATP, atmospheric pressure. What happens to the boiling point? Does it increase, decrease, or remain the same? Let me know in the comments. Which video do you want us to do next? Study the 3 organic reactions below. Compounds T and W are organic compounds. R and S are inorganic substances. Consider only the major products. Okay. So we're supposed to study these 3 reactions before we can actually attempt to answer the questions. So let's take a look and see what is happening. So we have HBr plus T, which gives us W. There's nothing we can really unlock here with that information. Let's take a look at reaction 2. Reaction 2, we have W, which reacts with NaOH to give us this compound that we have, which seems to be an alcohol. So already we can make sense of what is happening. We can determine T and potentially W. So let's take a look. So HBr, that is HBr is what we're adding to T, right? And then the product is W. And then when we add NaOH to W, of which what is happening here is a substitution reaction. We get CH3, CHOH, CH2, CH3, so on and so on. Because we know that W is saturated, right? It will be a haloalkane W, it seems. So if W is a haloalkane and we add NaOH, then reaction 2 is actually a substitution reaction. Okay, so W, can we write the formula for W? I think we can. W should be CH3, right? And then we have Br, and then there we go, the other 2 carbons. That makes sense to be W because we're going to replace Br with the OH, hence the product here. Right, let's carry on and deduce more things. So reaction 3, we have the product of reaction 2, some inorganic reactant S, and then we have H2O. So we've removed H2O in the reaction 3. So it means that T should be an alkene, and then reaction 3 should be dehydration, because one of the other product is H2O. So T is something like this. So 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. So this is T. This is T. This has to be T, right? But T is the same thing that we had in reaction 1. So we have W and then we have T. What is S? S is H2SO4, right? It's what we use when we want to dehydrate. And then R in that situation would be, so W, in W we have BR, and then, so it means R is NABR, because we added the OH there from NaOH. Okay, yeah, that seems good. So 4.1.1, the IUPAC name of W. So W is 2-bromobutane. Okay, and then 4.1.2, name of formula of R, NaBr. Okay, 4.1.3, two names of the type of reaction in reaction 1. So in reaction 1, we have an addition reaction, because T is an alkene, and all reactions that start with an alkene are addition reactions. But to be specific, is a halogenation. Yeah. To be more specific, it is a hydrobromination. Right. So I don't know where they want us to go there, but I think those are all the names for that reaction. 4.1.4, name or formula of S. S is H2SO4, like we've established. Okay, and then 4.1.5, we're looking for the structural formula of compound T. So yes, T. I'm just gonna add the hydrogens here. So yes, T. That is the structural formula of compound T. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. Okay, seems good. And then 4.1.6, W can be converted to T in one step. So we can go from W to T in one step. That would be dehydrohalogenation. True. So what is the question? States besides heat, one other reaction condition for this conversion. We need, so it is substitution, right? Is it? Let me check. So we're going from W to T. No, it's elimination. So we need a concentrated base. NaOH, KOH. Yeah. So that the K will take the Br and the OH will take the H, and then we're gonna have KBr and H2O as the other products. That is 4.1.6. Okay, and then 4.2. What is it been? 4.1.6. We have concentrated base. Okay, that is good. And then 4.2, a compound with the formula C10H22 undergoes a cracking reaction according to the equation. The mixture of the two compounds is bubbled in bromine water in a darkened room. Define the term cracking. I'll let you do that. 4.2.2, state one change beside a change in temperature that will be observed when the mixture is bubbled in Br2. The decolorization, right? Decolorization. I'm not sure. Yeah, it will decolorize. Yeah, because I think bromine water is greenish in color. So when it reacts with an alkene, of which 2x has to be, there will be a decolorization. It's a basic question. If you've done a lot of past exam questions, you should have gotten that question right. I've solved similar questions in the channel, obviously. 4.2.3, write down the structural formula of compound X. So let's determine what X is. So C10, so we have C10, and then we have C4. So how many carbons are we left with on the right that we need? We need 6 carbons on the right. So because we have the coefficient of 2 there, it means that this would be C3, so that 6 carbons plus 4 carbons gives us 10. And then we have H10 there, and then we have H here. And then on the other side, we have H22. So on the right-hand side, we are missing 12 carbons, but we have a coefficient of 2, so that has to be 6. So that is C3H6, which is plus C4H10. So the total number of carbons would be 10, and that of hydrogens would be 22. I'm happy with that. So structural formula of X. So X is unsaturated. There has to be a double bond. So 1, 2, 3. The position of the double bond does not matter because it would mean the same thing either way. So that's what we have. And then 1, 2, 3, 4. 1, 2. So let me check. This is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, happy with that structure of X. And then 4.2.4. Which compound X or C4H10 reacts faster with Br2? Explain the answer. This is the last question, so you know how we roll. You guys have to tell me the answer in the comment section. What is your answer to 4.2.4? Is it X or is it C4H10 that reacts faster with Br2? Why do you say so? Let me know in the comments. Carbon monoxide reacts with oxygen to form carbon dioxide. The graph below shows the concentration of O2 versus time. At which time, 10 seconds or 30 seconds, is the reaction rate higher? 5.2.1. Obviously, the answer is at 10 seconds. The reason being that at 10 seconds, we still have most of our reactants. And as the reaction progresses, the reactants get used up and the rate of reaction decreases. Right. 5.2.2. The reaction rate or the reaction takes place in a 3 decimeter cube container. Calculate the rate in mole per decimeter cube at which CO2 is formed in the first 10 seconds. So, a possible mistake that some people will make. Let's go. So, first and foremost, the rate of reaction will be equals to. So, because we are dealing with a graph of one of the reactants, we have to say minus the change in the number of moles divided by the change in the time. The change will be negative, so we need a minus sign so that they can be positive, right? And we're gonna have a positive rate of reaction. Our answer is gonna be positive, but we know what is happening. All right. So first and foremost, the SI unit that we're given is moles per second. So I then have to convert that concentration that is given to mole. So it's the first 10 seconds. So we're interested at this point and that point. Okay. The mark allocation 5 marks. So let's see. What we're going to do here, we're going to say the number of moles initial will be equals to, that is 0.27. 0.27. Maybe let me say n is equals to c multiplied by v first. So 0.27 multiplied by 3. So that is equals to 0.81. So we have 0.81. And number of moles final will be equals to 0.15. It's easy to see from the graph, right? Multiplied by 3, the volume. So that is 0.45. So the rate of reaction, therefore, would be minus. The final is 0.45. The initial is 0.81. Everything divided by the time. The time is 10 seconds. So we're going to have minus 0.45 minus 0.81 divided by 10. This is 0.036 mole per decimeter cube. There we go. Actually, we're not done. Back to the equation. Calculate the average rate in mole per second at which CO2 is formed. So that is what is easy to miss. We've used the information of O2, right? But then the balancing coefficient of O2 and CO2 differs. So this is the rate at which O2 is getting used up. It's not the rate at which CO2 is getting produced, or they say is being formed. But now that we have the rate at which O2 is being used, we can use the balancing coefficient. In chemistry, we can actually use, you know what you do with mole ratio when you want to find number of moles of one substance using the other. We can do the same thing, but using the rate of reaction. It works as well. So because, so we're saying that the rate of O2 is to the rate of CO2. This is 1:2. So the rate of CO2 therefore would be twice that of O2. So this is 0.072 moles per second. That is very easy to miss. That is very, very easy to miss. 5.2.2, let's do 5.2.3. Which reaction is in excess? Carbon monoxide or oxygen gas? So oxygen gas is in excess. The reason being that, take a look at the graph. The graph does not go to zero. So that tells us that actually the O2 is in excess. The carbon monoxide gets used up, and then what? And then the carbon monoxide gets used up, and then the O2 remains in the container, not getting used up. Hence, the graph does not cut on the x-axis. That is 5.2.4. Carrying on, 5.3. The reaction between sulfur dioxide and oxygen takes place in a sealed container according to the balance equation below. And then the question, was there a net release or net absorption of energy during the reverse reaction? So the forward reaction is exothermic, as we can see. So exothermic, that is where we have a release, right? So the reverse should be endothermic, where we have a absorption. So for the reverse reaction, we have a net absorption, right? And then 5.3.2, that's just a definition. 5.3.3, a catalyst vanadium pentoxide is added to the reaction. Explain in terms of the collision theory why the rate of the reaction will increase. A basic question, we are just singing a song that we have sung for a very long time. When you add a catalyst, the activation energy decreases. Then more particles, more molecules will have a kinetic energy that is greater than or equals to the activation energy. More effective collisions per unit time, rate of reaction increases. Same song, right? Curve X is the Maxwell-Boltzmann distribution curve for the reaction above. Okay. More CO2 is now added to the container at constant temperature. So the temperature remains the same. Why was that key? Why did they deem it necessary to tell us that? Okay, but stories 5.3.4. How will this change affect the heat of the reaction? Choose from increases, decreases, or remain the same. It shouldn't be a grade 12 math and science video if you don't have to give some answers as well. So 5.3.4 in the comment section, let me know. Increases, decreases, or remains the same. Increases is not an option. 5.3.5, redraw the above graph in the answer book. On the same set of axes, draw the curve that will now be obtained. Label this as curve Y. Okay, let's pay attention again. What is happening? More CSO2 is now added in the container at constant temperature, or SO2, one of the reactants. and then the curve that will be obtained. So the only thing that we are increasing is the temperature, is the number of particles of SO2. So we're gonna have the identical graph, but now it just has like a higher peak. Yeah, we have like identical thing, but just above that one. Sticking to the basics, really. There we go. A few drops of concentrated hydrochloric acid are added to the equilibrium mixture. What effect does this addition have on the mass of CaOH2? Choose from increases, decreases, or remains the same. Okay, so let's take a look. HCl gives us H plus Cl minus, right? So what is going to happen here is that the H plus and the OH minus will react, and then as they react, it means that the amount of OH minus goes down. If the amount of OH minus goes down, then the system will want to reinstate a new equilibrium by opposing the change, right? By favoring the reaction that opposes the change. So since the amount of OH minus is decreasing, the system is actually going to favor the forward reaction so that OH minus can increase as it is decreasing. So what is the equation saying? What effect does this addition have on the mass of CaOH2? Well, it decreases. And then 6.1.3 is saying let's use Chattelier's principle to explain the answer to 6.1.2, which I just did. H plus will react with OH minus. The amount of OH minus, the concentration decreases. If it decreases, the system wants to reinstate a new equilibrium by favoring a reaction that opposes the change. Hence, forward reaction is going to be favored. The mass of CaOH2 will decrease. That is 6.1. 6.2. Initially, 70 grams of NH4HS is placed in a 3 decimeter cube container at 250 degrees Celsius. The container is sealed and the reaction is allowed to reach equilibrium according to the balance equation. The Kc values for the decomposition of NH4HS at different temperatures is given in the table below. 6.2.1 is the decomposition of NH4HS and exothermic or endothermic reaction. So let's take a look at the table that we have. As the temperature increases, the Kc increases. Kc increasing implies that the amount of products is increasing. If the amount of products is increasing, then the forward reaction is favored. So let's take a look at what causes an increase in the Kc. An increase in temperature is causing an increase in the Kc. So that tells us that the decomposition of NH4HS is an endothermic reaction, because we know that an increase in temperature favors an endothermic reaction. And clearly here, when the temperature is increased, the forward reaction is favored, leading to an increase in the Kc. 6.2.2, we're supposed to explain that using Chattelier's principle, which I just did. And then 6.2.3, calculate the mass of NH4HS that will be present at equilibrium at 250 degrees Celsius. So let's stick to the basics. We need our table, right? So rice, some people call it, seems to be popular. Let's just go with that. So this is NH4HS, NH3, H2S. So we want to calculate the mass. We're given the Kc. So we need to fill the table and set up a Kc expression, substitute, and we're going to have the mass. So initially, the mass of NH4CS is 70 grams. I don't want to substitute 70 grams there. I want to substitute the number of moles. So I want the number of moles of NH4CS. Let me take out my periodic table. NH4 HS, so I already have 5 hydrogens, 1 nitrogen, which is 14, plus sulfur, which is 32. So the molar mass is 51. So I have 70 over 51, which is 1.3725. I want my answer to be as accurate as possible, so I'm going to leave it at 4 decimals, which I always advise. Trying to do something here, but it's not working. Okay, where's my table? Right, let's carry on. So that is the mass we have initially sealed. So we have 0, 0, 4, NH3 and H2S. And then, oh, okay, I'm supposed to have the ratio actually there and not these numbers. 1.3725. 1.3725. 0, 0 is there. Here I'm supposed to have the ratio, of which is the balancing coefficient. 1, 1, 1. So the change here would be minus x, here it will be plus x, here it will be plus x, as you know it decomposes. So at equilibrium we would have 1.3725 minus x. This is x, this is x. Are we given the volume? Let me check. The volume is 3 decimeter cube. Okay, so the concentration we just divide by the volume, right? Divided by 3, divided by 3, divided by 3. Okay, so that's what we have. We can set up Kc then. Okay, so Kc is equals to NH4 HS is a solid, so we're gonna have NH3 H2S, and then in place of NH4 HS, that is gonna be 1. Yeah, that's what we do. So the Kc at 250 degrees Celsius is 18 times 10 to the minus 2, and that is equals to well, x over 3 x over 3. Right, so we're gonna have 18 times 10 to the minus 2 being equals to x squared over 9, right? So 18 times 10 to the minus 2 multiplied by 9. 1.62. So 1.62 is equals to x squared. So square root on both sides. X is equals to 1.2728 watt moles. Yes, moles. So that is x. So at equilibrium, we're looking for the mass of NH4 at equilibrium. So the number of moles at equilibrium, we have 1.3725 minus 1.2728. 1.3725. The answer is 0.0997 moles at equilibrium. So the mass, therefore, right, just substitute there. So multiplied by the number of moles multiplied by the molar mass. What is the molar mass again? I forgot. Okay, but it's fine. I'm just gonna add. Nitrogen is 14, 5 hydrogens. That is 5, and then sulfur is 32, and the mass at equilibrium it's 5.09 grams. 7.1 phosphoric acid is an example of an acid that, you know what, let's just do 7.2. It's fine. Barium hydroxide dissolves in water according to the balance equation. A 100 centimeter cube solution is prepared by dissolving an unknown amount of BaOH2 at 25 degrees Celsius. 25 centimeter cube of the BaOH2 solution is reacted with 15 centimeter cube of a 0.2 mole per decimeter cube HCl solution in a flask according to the balance equation. The final pH of the solution is 12.62 at 25 degrees Celsius. So first of all, let's conceptualize. Let's have a sketch of what is happening. So we have this 100 centimeter cube of an unknown amount of BaOH2, right? Of this 100 centimeter cube, we take 25 centimeter cube and then we react it with HCl. That is what these points are saying. And then the final pH of the solution is 12.62 at 25 degrees Celsius. That tells us something. That tells us that the base is in excess. So of that 25 centimeter cube, the base that is in there remains. So HCl is the limiting, the base is in excess. And then the base has some pH. We don't know the actual amount of the base, but we know that the pH is 12.62. This is the pH of the base that remains. Okay, so 7.2.1, calculate the final concentration of the hydroxide ions in the flask. So the question is saying, let's calculate how much OH minus we have at this point in the excess base. We are looking for the concentration of OH minus in the excess base. Okay, so 7.2.1, let us do that. So the pH is equals to 12.62. We know that the pH plus the pOH is equals to 14. So the pOH is equals to, so 14 minus 12.62, that is 1.38. But by formula, the pOH is minus log of OH minus, and then this is equals to 1.38. So the concentration of OH minus is 10 to the minus 1.38. So let me put that in my calculator. 10 to the minus 1.38. This is equals to 0.04. Okay, this is my final answer, so I can leave it here. 0.04. Let me just say 0.04 to 2 decimal places, 2 significant figures. That is mole per decimeter cube. That is the amount of hydroxide ions in the flask that are in excess. Okay, and then 7.2.2, we are looking for the number of moles of the base used to prepare the 100 centimeter cube solution. So let's come back here to our sketch where we are conceptualizing. So we know the number of moles, not the number of moles, but the concentration of OH minus that remains. So we have OH minus here. We have the concentration of OH minus. So with this concentration of OH minus, what we want to do is to calculate the number of OH minus that are in the flask at the end. Because if we calculate the number of OH minus that are in the flask at the end, we are then going to be able to calculate the number of moles of the base that are in excess, right? We're going to be able to calculate the number of moles of the base that are in excess. So that's what that information is going to allow us to do. But we know how much the 25 centimeter cube of base reacted. We know the amount of acid that reacted with the 25 centimeter cube of the base. It is 15 centimeter cube of a 0.2 mole per decimeter cube concentration. So we can calculate the number of moles of base that are in excess, right? And then using the acid, we can calculate the number of moles of base that reacted. So we will be in a position where we have the number of moles of base in excess, the number of moles of base that reacted, so we can find the initial. Let's go. So we ended up saying that the concentration of OH minus is equals to 0.042 moles per decimeter cube, obviously. We can then calculate the number of moles of this OH minus. The number of moles of OH minus is equals to C multiplied by V. The concentration is 0.042. And exactly at this step, we are losing some people. The volume is 25 plus 15 because the volumes are additive, right? This is times 10 to the minus 3. I have to convert it to decimeter cube. Yeah, the volume of the acid plus the volume of the base will be the total volume at the end of the reaction. So 0.042 multiplied by 40 essentially, multiplied by times 10 to the minus 3 to convert it to decimeter cube. This is equals to 0.00168 moles. Those are the number of moles of OH minus. But we know that BaOH2 is just Ba to the 2 plus, I would like to believe, plus 2OH minus. So if the number of moles of OH minus is 0.00168, then those of the base should be half that. Those of the base should be half that because of the balancing coefficient. We have a 1:2 relationship. So if we have 0.00168 then the number of moles of the base is 0.00084. These are the number of moles of the base that are in excess. Those are the number of moles of base that are in excess. Now let's find the number of moles of the base that reacted. We're going to use HCl, by the way. So N is equals to C multiplied by V. We're calculating the number of moles of HCl here, which will be 15. No, that is the volume. The concentration is 0.2. The volume is 15 over 1000. So when I put that in my calculator, this is 0.003. 0.003. So now looking at this reaction, the balancing coefficient is a 1:2 relationship. So if the number of moles of acid are 0.003, then those of the base will be 0.0015. So these are the number of moles of the base that reacted, right? So the number of moles of the base initially, therefore, will be equal to those that reacted plus those that are in excess. So 0.0015 plus 0.00084. Another 0.84. Right, so that will be close to. Let me just put that in my calculator. 0.00084. There we go. Number of moles of base 0.000234 moles. Right, so these are the number of moles of base in 25 centimeter cube. There's still one more step that we need to do. So these are the number of moles in 25 centimeter cube. We need to find the number of moles of base in 100 centimeter cube. So how many 25 centimeter cubes do we have in 100? We have 4. But we can just say 0.00234 multiplied by 100 over 25. Right, using 25 here, just in case you find yourself in a scenario where you have 37.163, you can just multiply the total volume which you have started with divided by that which was used, so that you can find the number of moles in total. So let's see, 0.00234 multiplied by 4. So the number of moles of base in 100 centimeter cube is 0.0094 moles. There we go. 8.4. Calculate the mass needed to prepare 250 centimeter cube of this solution so that the cell operates initially under standard conditions. There's a twist to 8.4. Let's do 8.2 first. Which ion concentration, Al to the 3 plus or zinc to the 2 plus, will increase? Give a reason for the answer. So first things first, we need to determine what is at the anode and what is at the cathode using our table of standard reduction potentials. So you should realize that aluminum is at the anode, right? And then zinc is at the cathode. So at the anode, this is what is happening. We have aluminum becoming Al to the 3 plus 3 electrons. So the concentration that increases is therefore that of aluminium 3 plus. Why is that the case? As oxidation is taking place, the concentration of Al to the 3 plus in the electrolyte will be increasing while the electrons migrate to the cathode through the voltmeter. 8.3. Write down the cell notation for this cell. The electrolyte in the aluminium half cell is I'm moving to 8.4. 8.3. Write down the cell notation for this cell. So we know that this is the oxidation half reaction, and then the reduction half reaction is zinc 2 plus some 2 electrons giving us zinc. So salt bridge, what is happening at the cathode? Zinc 2 plus accept 2 electrons to become zinc. What happens at the anode? Aluminium undergoes oxidation to become Al to the 3 plus. So take a look at that. That is our cell notation. Obviously, we can include the phases. 8.3. Now 8.4. This is the mistake that most people are going to do. So we are looking for the mass of that compound needed to prepare 250 centimeter cube of this solution so that the cell operates initially under standard conditions. So the standard condition of interest is that the concentration is 1 mole per decimeter cube. Right, and then we have the volume, which is 250 centimeter cube. We can obviously calculate the molar mass of that compound. So we are interested in the mass. There's still a mistake that people are going to make. Just follow through. Let me show you something. So we say C is equals to the mass divided by the molar mass multiplied by the volume. The concentration is 1. The mass is what we're interested in. And then the molar mass, I had written it somewhere. Let me check that. The molar mass is 342. The volume is 250 divided by 1000. So we cross multiply. The mass is going to be equals to 342 multiplied by 250 over 1000, which gives us 85.5 grams. Right, so this is where a lot of people are going to end. But the story carries on because, take a look at this. Aluminium 2SO43 dissociates to give us 2 aluminium to the 3 plus 3 SO4 to the 2 minus. Right, so take a look at this. If the concentration of Al2SO43 is 1 mole per decimeter cube, the concentration of Al to the 3 plus will be 2 moles per decimeter cube because of that relationship. And it is the concentration of Al3 plus which we're interested in. We want that concentration to be 1 mole per decimeter cube. So actually the mass that gives us 1 mole per decimeter cube should therefore be half of what we have calculated initially. So therefore the mass which we are actually looking for will be our answer divided by 2, which is 42.75 grams. Did you realize that? Did you realize that? Or you missed the point? Let me know in the comments. Here we go. Is this an electrolytic cell or a galvanic cell? 9.1. Obviously, this is an electrolytic cell. You know, one of the reasons being that we have a power source. 9.1. 9.2. So let's go back to the question statement and see what is happening. The diagram below represents a cell used for the refining of copper. So we have electrode Q and R and the electrolyte. The unrefined copper contains zinc as the only impurity. So let's make sense of the situation. We need to figure out what the anode is and what the cathode is. So let's see. We are refining copper. So we have unrefined copper at one of the electrodes. So we need the unrefined copper at the anode actually. We need the unrefined copper at the anode so that oxidation can take place and then copper can get deposited at the cathode. So in an electrolytic cell, obviously we have a positive terminal here, and the negative terminal. So in an electrolytic cell, where do we find the anode? Is it at the positive terminal or is it at the negative terminal? We find the anode at the positive terminal. That is true for all electrolytic cells. So we know that here we have the impure copper, so to say, right? And here at electrode Q at the negative terminal, we have the cathode, so impure copper at the anode, and here we have the cathode. So we need to be able to deduce that. Right, now the question: when the switch is closed, it is found that after T hours, what are they saying? When the switch is closed, it is found after T hours that the amount of copper 2+ ions in the electrolyte changed by 0.05 moles and 0.15 moles of copper were deposited on electrode Q. Okay, it's fine. And then 9.2.1, how will the concentration of zinc ions in the electrolyte be affected during the refining of the copper? So obviously the answer to 9.2.1 is that it increases, right? The concentration of zinc ions increases in the electrolyte, because at the anode, where we have the impure copper, we have two oxidation reactions taking place. Essentially, we have copper becoming copper 2+ plus 2 electrons, and then we have zinc becoming zinc 2+ plus 2 electrons, but only copper 2+ goes to the cathode. So with that said, the zinc 2+ will be in the electrolyte, so the concentration is increasing in the electrolyte during the refining of copper. So that is 9.2.1. And then 9.2.2, will the amount of copper 2+ ions increase or decrease? Explain the answer in terms of the relative strength of the oxidizing agents. That is 9.2.2. So the answer here is decrease, right? The amount of copper 2+ will decrease in the electrolyte. So why is that the case? We have copper 2+ and zinc 2+ in the electrolyte, right? And then one between these two has to go to the cathode and get reduced, right? So that is why the question says explain the answer in terms of the relative strength of the oxidizing agents present. So we have copper 2+ in the electrolyte, and we also have zinc 2+. So strength of the oxidizing agent. So let's go back to the basics. The oxidizing agent wants to get reduced. That's what we have to comprehend. The oxidizing agent is what gets reduced, and then the reducing agent is what gets oxidized, right? So copper 2+ and zinc 2+ are our two oxidizing agents, but copper 2+ is a stronger oxidizing agent compared to zinc 2+. So copper 2+ gets reduced to form copper at the cathode. So the concentration of copper 2+ will decrease, right? So that is 9.2.2. And then 9.2.3, calculate the change in mass of electrode R after T hours for 6 marks. So let's take a look at this. So we have our reaction taking place, obviously. We have oxidation taking place, and then we have some zinc 2+ in the electrolyte, and then we have copper 2+ in the electrolyte as well. But what we know is that the copper 2+ is what's going to get reduced at the cathode to form copper. So let's make sense of what is happening. So the amount of copper 2+ in the electrolyte changed by 0.05. Okay, so let's write that down. So by 0.05 moles, that is. So the number of moles of copper 2+ in the electrolyte they change by 0.05 moles. Okay, and then the second step, we are told that the number of moles of copper, not copper 2 plus, but the number of moles of copper that were deposited at in the electrode Q, which is our cathode, is 0.15 moles. Right, so let's make sense of this. In the electrolyte, there is a change of 0.05. So what does that tell us? It tells us that 0.05 moles of copper 2 plus that were deposited in the cathode were coming from the electrolyte. So we have a total of 0.15 moles at the cathode. 0.05 moles are coming from the electrolyte. Someone is trying to call me. 0.05 is coming from the electrolyte, and 0.1 mole, therefore, to give us the total of 0.15 that was deposited at the cathode. So the 0.1 is what's coming from the anode, therefore this is what's coming from the anode. Right, so the 0.05, it comes from the electrolyte, and then the 0.1 mole comes from the anode as oxidation is taking place. Right, but not only is we know that at the anode there's two reactions taking place, right? There's zinc becoming zinc 2 plus, and there's copper becoming copper 2 plus. All right, and then the rate of oxidation is equal to the rate of reduction. We need to remember that as well. The rate of oxidation is equal to the rate of reduction. So at the electrolyte, the concentration of the electrolyte is to remain the same, right? But then we have 0.05 moles of electrolyte that is being used of copper 2 plus. So how is the concentration of the electrolyte remaining the same? Therefore, this is replaced by zinc 2 plus. So the number of moles of zinc 2 plus in the electrolyte is 0.05 moles. Right, so it means that at the cathode, not at the cathode, but at the anode, we lost 0.1 moles of copper at the anode, and then we also lost 0.05 moles of zinc at the anode. So that's what we lost. We lost 0.1 moles of copper and 0.05 moles of zinc. Right, but the question says calculate the change in mass of the electrode R after T hours. So now that we have the number of moles of copper and the number of moles of zinc, we can just go ahead and calculate the mass of the two. So the mass of copper, obviously number of moles multiplied by molar mass. So this is going to be 0.1. So my periodic table, what is the molar mass of copper? 63.5. So this is going to be 6.35 grams. So that is the mass of copper. And then the mass of zinc, that is going to be equals to 0.05 multiplied by molar mass of zinc. I'm literally looking at the periodic table here. 65. Right, so let me put that in my calculator. 0.05 multiplied by 65, that is 3.25. So the mass of zinc is 3.25 grams that we lost at the anode. So calculate the change in mass in electrode R, right? So the change in mass therefore will be 6.35 plus 3.25. So plus 6.35. This is 9.6 grams. Calculate the change in mass in the electrode. So there's a decrease of 9.6 grams at the electrode R, which is our anode. Here we go.